In this section, we will study the dynamic response of second-order systems. Let's start with the second-order system with real poles. So let's assume the transfer function. The denominator is s plus alpha 1 times s plus alpha 2. Let's assume there are no zeros. So the numerator is just a constant, but then to calculate the impulse response, we know the Laplace transform of the impulse signal is 1. Therefore, the impulse response can be calculated by using the inverse Laplace transform to the transfer function. Then we can write the transfer function in the partial fraction expansion form. Since there are two poles, so the transfer function can be written as C1 or S plus alpha 1 plus C2 or S plus alpha 2. So C1, C2 are just some constants, so we can use the co-op method to determine C1 and C2. So C1 and C2 can be determined by alpha and beta. Now, let's assume alpha 2 is greater than alpha 1. Greater than 0. Therefore, we know the system is stable. So if alpha 1 or alpha 2 is less than 0, then we know the system is unstable. So it's meaningless to study the dynamic response. If we draw the S-plane, the real part, imaginary part, have minus alpha 1 and minus minus 2. Then when we apply the inverse Laplace transform to the partial fraction expansion form, then we know the impulse response. It has two components. The first component is the inverse Laplace transform of the first term. It will be C1 exponential minus alpha 1t plus the inverse Laplace transform of the second term. It will be C2 exponential minus alpha 2t. Since minus alpha 2 is further to the left, then we know the second term decays to 0 faster than the first term. So in general, if the poles are further to the left, the corresponding components decays to 0 faster than the poles which are close to the imaginary axis. Then we can call the pole to the left is faster pole. We can also see that the impulse response of a second order system is just the sum of the impulse responses of two first order systems. So the first term can be considered as the impulse response of a first order system. Then the second component is the impulse response of this first order systems. Now let's see one example. Let's find the impulse response of this transfer function. We have 2 over s squared plus 3s plus 2. First, let's find the poles of this transfer function. To find the poles, we can write the denominator as s squared plus 3s plus 2 is equal to s plus 1 and s plus 2. Therefore, we know the transfer function has two poles. One is -1, another is -2. -1 and -2. -1, -2, -1. It has no zeros. Then we can apply the partial fraction expansion. We have C1 s plus 1 plus C2 s plus 2. To calculate C1, we can use the cover-up method by the C1 so we multiply, so both sides of s plus 1, then let s be minus 1. C1 2 s plus 1 s plus 2. If we multiply s plus 1, let s be minus 1. Then we can cancel s plus 1. If s is minus 1, then we know C1 is 2. Similarly, we can get C2 by multiplying S2 on both sides and let S be minus 2. So C2 will be 2 S plus 1 S plus 2. We multiply S plus 2 then let S be minus 2. We have S plus 2 is cancelled. If S is minus 2, so C2 is minus 2. Then we apply the inverse Laplace transform, so we can get the time function. The impulse response is 2 exponential minus 2 minus 2 exponential minus 2t. Then we can use MATLAB to draw the impulse response. So this plot shows the impulse response of this transfer function. So at beginning when t is 0, so both components are 0. So the impulse response starts at 0. With the increase of t, because the second term decays faster than the first term. So the impulse response is always greater than 0. At the beginning, the difference between the two components increases with the increase of time. And up to some point, the difference between the two components decreases. And eventually, the difference will be 0. And the impulse response will decay to 0 eventually, because we have two poles on the left half of the S-plane. It means the system is stable. If the system is stable, the impulse response will decay to 0. That is the definition of stability.